So the first law of thermodynamics tells us that the energy in both the system and surroundings together is conserved. Now, whenever we talk about energy of a system, there's actually going to be different types. All right, so the total energy of system includes different types. Okay? And in this course, we're going to consider specifically 3 types of energy. Consider 3 types of energy. Okay? And so the 3 types are going to be kinetic, potential, and internal. Okay? Now, the first 2 are things you've seen before. Not only in your Physics 1 class here in college, but likely in your physics class in high school as well. Okay? And so let's begin with the first 2. So kinetic energy, the way that I'll define it is that it's the energy of a system based on its velocity. Energy of system based on its velocity. All right? But its velocity relative to some frame of reference. Okay? Right? And so, for example, we could say whenever we report the velocity of a car, and saying it's going this fast in this direction, we're implicitly using the Earth's surface as the frame of reference. Okay? Now, the way you calculate kinetic energy depends on whether you're working with closed systems or open systems. Let's begin with the closed system. Okay? And so, if we're dealing with closed systems, the kinetic energy, which I'll symbolize as this E sub k, is going to be calculated using the formula you remember from your Physics 1 class. So it's going to be 1/2 times mass times velocity squared. All right, and I'm going to use the letter U for velocity in this course. All right. So that's the kinetic energy. Let's now consider the units of this kinetic energy term. Okay? All right, and so just based on the fact that we have mass times velocity squared, that means that our dimensions for the kinetic energy is going to be equal to mass times a length squared over time squared. Okay? And so kinetic energy, as the name implies, is going to give us units of energy. So for example, in the SI units, one unit that describes energy is a joule, right? Which is equal to a kilogram times meter squared over second squared. Okay? So mass, length squared over time squared. All right, so a kinetic energy term in a closed system should give you units of joules if you're working in SI. All right? And so this is for a closed system. Now, if we're dealing with an open system, rather than calculating an energy, what we're going to calculate instead is an energy rate. Right? And so a kinetic energy rate, which I symbolize as E sub k with a dot on top, is going to be equal to 1/2 times a mass flow rate, so with a little dot, times the velocity. Okay? And so here, if we consider the dimensions of our kinetic energy rate, what we'll have instead is mass times length squared over time cubed. All right? And so if we're dealing with SI units, what we could conceivably end up with is joules per second, right? Which is equal to a watt. All right, and so, as you remember from Physics 1, a watt is a unit of power. And so, when I say we end up with a kinetic energy rate here, anytime we're dealing with energy rates, we're talking about power. Okay? All right, and so this is kinetic energy. You calculate it using formulas you've seen before, or similar formulas. Okay? All right, the next thing we'll talk about is potential energy. All right, and so the way I'll define potential energy is it's going to be the energy of a system that's due to a force that's exerted on it. So energy of system because of force exerted on it by a potential field. Okay? And so some examples of this, just to make this a bit more concrete, is the force that's exerted on a system due to the fact that it's within a gravitational field. Right? Or if you're dealing with, electromagnetic things, the force exerted on something because of an electromagnetic field. Okay? And once again, this is all relative to some reference surface. Okay? All right, and so the way that you calculate the potential energy for a closed system, so E sub P, is going to be equal to your mass times gravity divided by your GC, right, which helps you get everything in the correct units, and then times a height, Z. Okay? And so Z here is height with respect to some reference surface where you consider the potential energy to be equal to 0. Okay? All right, and so when you calculate this potential energy for a closed system, the dimensions of your potential energy should once again be mass times the length squared over time squared. Okay? So if you're in SI units, this would give you a joule. All right, for open systems, we once again will have to deal with an energy rate. Okay? And so for open systems, the potential energy rate is going to be a mass flow rate times your G over GC times Z, which is that reference height. Okay? And the dimensions for this will once again be mass times length squared over time cubed, which if you're dealing with SI units, this will give you a watt. Okay? So once again, the potential energy rate gives you a power. Okay, so kinetic and potential energies are concepts that you've already seen before. So these are the first two types of energy that we'll discuss. The last type of energy that we'll discuss in this course is called internal energy. Okay? And we're going to symbolize it with a capital U. All right? Okay, and so really a kind of very brief definition of internal energy is it's any sort of energy that is not kinetic or potential energy. Right, so basically this is the everything else energy. Right. For a more precise definition of internal energy, we could think of it as the energy that accounts for, you know, molecular, atomic, or even subatomic uh, processes within our system. So it accounts for molecular, atomic, and subatomic energies of a system. Okay? Alright, one useful thing or feature of internal energy is that it can be stored. Right? And this is useful if you think of a battery. Right? So that way you could store energy within some sort of material and then easily transfer that energy so that it could be used by some other sort of process. Okay? All right. Now, the tricky thing about internal energy is that we can't directly measure it. Right? You know, we don't have an internal energy meter. Right? And so, in order to at least characterize or quantify the internal energy of a system, what we have to do is we have to calculate it using, you know, thermodynamic models that are based on variables that we can measure, specifically pressure, volume, and temperature. Okay? All right, and so for now, all I'll say is that we're just going to learn more about this concept later.